The last part of this lecture is how to bias differential pairs. So differential pair, we have it here, the small signal path, and we'll see how we connected the transistors for differential configuration, fully differential configuration, and then when we put the bias transistor, it will look like this. Okay, so then we have to do the reduction exactly as we did before. Then when we move the gate source on the input towards the drain and the source, we will have the following, and then this will cancel at the sources, and then at the outputs also we will see that basically when we measure it, the outputs that will also be cancelled. So what we will have left, it is just the current sources. So we're going to split the current sources, and then we can use that third point, the ground point, and then we will have the following resulting circuit here. And then we introduce the point VDD, and then we split the current sources also the input, so we will have the following, and then this node here, this node here, it is called this node that is VDD. We have that this current source and this current source are not part of our circuit anymore. They are in parallel to VDD. They are current sources in parallel to VDD, so we can just delete them, and what we have is the next circuit. Yeah. Okay, so this is the way to bias a differential pair, in which we have the outputs taken like this with a high impedance. Okay, so now the issue that we have here is that these current sources will be implemented with PMOS transistors, and this current source here will be implemented with NMOS transistors. Sometimes we might use resistors as loads in the differential pair, and that is perfectly okay in some applications, but very often we will use current sources. And then the issue here is that when we implement current sources with different types, they will just not match. There will be a mismatch between these two current sources, and the mismatch in the current sources cannot be controlled. We cannot just leave them without control, because in reality voltage, temperature, and process variations will just make them that in real operation they will not match. One current will be slightly different than the other, and if this current here it is just higher than these ones, then basically the outputs will be pulled either up or down. If the current is larger, or the NMOS, the output nodes will be pulled down, and vice versa. If the PMOS current sources are stronger, it's more current, so this node will be pulled toward VDD. So yeah, we need to introduce a mechanism that controls exactly the DC level of the output, and that mechanism is called the common mode feedback. The common mode feedback, and the implementation of the common mode feedback is very similar to what we did in the additional feedback loop that was required to bias this transimpedance amplifier. So we will need some correction amplifier in which we insert, we connect a reference voltage, and then we feedback to some point in the circuit that bias the differential pair. So the input to this correction amplifier will be the average of the outputs of the differential pair. So we need some circuit that extract the average, and we have a comparison with our reference voltage that we want to have it here in these nodes, and then there is a correction going that controls either the NMOS or the PMOS current sources. There is not really much difference which one control. So these are going to be basic ideas for implementing a common mode feedback loop, and there are many implementations. The one that I'm going to show you, it is probably the simplest one. Okay, so the example that I'm going to show you, it is also transimpedance amplifiers, a single stage transimpedance amplifier, but this time is a differential. It's a differential transimpedance amplifier. So if we draw it like let's draw it like a nuller. If we draw it like a nuller, it will look like this. Okay, so we have the following model here. Okay, so we have our source here, and then we will have the feedback transistor. So it works very similar to the single-ended, no? So, but in this case, the current we have a differential current flowing in this direction. Okay, now the common mode, it is not fixed in this implementation. We need to do that, and for that we need to add common mode feedback. So we have some load, capacitive load here that we have here. The capacitive load, the core of the transimpedance amplifier is here, and then what do we do here? First, we need to extract the average of this circuit, and one way it is just let's draw it again here, the differential amplifier like this, and with the current sources here. So one way it is just to use two resistors, one resistor here, and then just connect it here. And then when the signal goes up and down in one side, it is going down and up in the other side. Basically, the node in the middle can be considered the addition of these two, and then the sinusoidal part is basically subtracted here in the middle, and the only thing that it is left, it is the common mode. So this circuit works like an adder. So this circuit, it is very simple because it requires only two resistors. The problem is that it is loading the output here, so we cannot use it directly. In most of the cases, we cannot use it directly because it just reduces the gain of the core. So what we actually can do here, it is instead of using like this, we will have to use extremely large resistors there in order not to load the output of the amplifier, but instead what we can do there, it is to use a common drain amplifier. So we can do like this. We use common drain amplifier that only have a capacitive input. So there's only some capacitive input that is capacitance that is going to be loading, and then we have the two resistors here getting the average. So here we have the average, and then as explained before, we need only the DC. We need to filter. In this case, it is already DC. We can already use it as it is, but very often we put another capacitor here. And the reason for that is that we might want to have a very well-defined pole here, typically a dominant pole here, pole close to DC. So large resistors here, and with a capacitor, they will place a dominant pole. Remember that we don't want very large gain in this circuit. We want very small gain. So we are just amplifying DC signals, so we are just processing DC signals, and then it is going to the correction amplifier. Going to the correction amplifier, we have a reference voltage, and then this is going to control either up or down, here and here. Okay, so the implementation is here. The implementation is here again. In this case, it is just the finalized circuit. In practice, we have to do exactly what we did for the amplifier. Put this in small signal and check the stability of the loop, extract the loop gain, etc., etc. We can, if needed, we can use the compensation method that we studied before. When we have the capacitor here, we have the possibility to do pole zero compensation. So we place a low frequency pole, and then if we put a resistor in series, we create a zero, and then we can put this zero over another pole to improve the stability. For the amplifier, very simple amplifier, differential amplifier with active loads and diode connected loads. The diode connected load, it is very important because the gain of this amplifier, it is very little. The gain of the amplifier, it is approximately the gain of these transistors. These are M13 or M14 times the load here. So the load, it is very small because it is, in this case, it is just 1 over GM12, and then the gain that we have here, it is very, very small. This is approximately 1. And in practice, we can even delete this one and connect this to VDD, but for symmetry purposes, and if the transistor is very small, you can always keep it like that. So I think this is really not doing much, this transistor. And then the trick here, not the trick, but I think the most important detail is these transistors and these transistors. The sizes of these transistors are very, very important, and they are pretty much related. So you have this current here, we call it I1. You have the current here, I1 divided by 2. Okay, so this is I2, and this is basically a current mirror. This is a current mirror, so this will be I1 divided by 2 times M, and this is the current that I want to pass here. So I dimension this one, I dimension this current based on the current that I want to pass here. Then I can decide which current to use here. And again, the current that you want to have it here, it has to be very, very, very small in comparison to the current that we have here. So you can dimension the ratio of this transistor. The length have to be the same, and you dimension the current mirror. So let's take a look in Cadence exactly how this is working. So we have So we have our circuit here. Okay, and just run simulation. And we check that VOP is the output voltage and then the positive output, and the negative, they are basically the same. Yeah. We put 100 kilo ohm resistors there, and the result is 75 kilovolt, and yeah, the reason for that is that it is just a single stage amplifier, so there is no lot of loop gain there in this particular case. Then I just run a transient, but I run a transient on the step because I am interested to know what happened with the stability of my common mode feedback, the stability, and then we can see that the node C is the is at the output of the average circuit, the one that it is coming to the correction amplifier, and yeah, so basically this is what it is coming back to my correction amplifier. I set the common mode feedback at 600 millivolts here, and then the common mode has to be set to around 600 millivolts also. And when I oh, sorry, no, terrible mistake. We have to take the we have to annotate the operating points. Let's see, results, annotate. Oh, it didn't go. Let's see, annotate. Oops. Same DC operating point. Okay, now let's see the results. Annotate. Now it's working. DC operating point. Annotate. Okay. Okay, so we have that. Yeah, if I want 1 volt at the output, then I cannot put 1 volt in the common mode feedback, and the reason for that is that the common drains will consume some voltage drop. There is a BGS that in this case has around 400 millivolts, so I will have to adjust for that, and that is the problem with this biasing. The common drains will have a voltage drop, so they are not very amenable for a very low voltage operation, this common mode feedback, but otherwise it works very nicely. It's very simple to implement. So what I put here is 600 millivolts in this reference that I want, so I expect 600 millivolts coming from the average circuit, and then the DC level is almost 600 millivolts as I expected. So there is a very good loop gain, very little variation between my reference and the voltage that I expected, and then at the outputs it is very very much what I expected, 1 volt. Okay, and I check the stability of the circuit. I run the transient and stability simulation to check that it is stable, and then I can get the loop gains and phase here, and then we can see that my common mode feedback, it has around 54 degrees margin, which it is very good. And we can see that when we put a pulse at the reference, and then see that it recovers quite quickly and without a large overshoot. Okay, and I think that is the last example. That the current. Now, the current that I have in this case, it is around 1 microamp here, so it is going to pass around half a microamp in this diode connected, and here we will pass 5 microamps. So there is a 10-to-1 ratio between these two transistors, so I keep the lengths the same. The lengths were 2 micrometer, and then I just use a multiplier by 10. So it is very important this. So the current ratios and the sizes have to be chosen very carefully, so that the circuit is basically produce it stabilizes in the right operating point. Half of the current flowing in one transistor, half in the other. And okay, there is not much gain here in this amplifier, so the chances that it introduces instability problems are quite low. So it doesn't add more gain that the gain that we already have. In a more complicated amplifier, for instance, a 2-stage amplifier, or using a cascode, there will be much more gain. So we definitely don't want to add more gain in the correction amplifier. We just need to do the comparison and then set the right currents at the amplifier. Okay, so with this example of a differential amplifier, we finished the class on biasing.